and thank you for joining us this evening. I am Omar Hatamli, the Program Director for the International Space University Space Studies Program 2017. And before we begin, I would like to remind you, please, to put your phones on silent. And in terms of emergency exit doors, we have one on the left, one behind me on the right, and there is one across the door here. There will be an opportunity for questions at the end of the talk, so we'll be giving the mics, and somebody has a question, please raise your hand, and somebody will bring the microphone for you. So tonight, the International Space University Space Studies Program is happy to invite you to a distinguished lecture by astronaut Jeff Hoffman. Dr. Jeff Hoffman is a professor of aerospace engineering at MIT in Boston. And he received his PhD in astrophysics from Harvard University in 1971. Dr. Hoffman is actually made 5 space flights, becoming the first astronaut to log over 1,000 hours of space flight aboard the space shuttle. He had also performed 4 spacewalks, including the first unplanned contingency spacewalk in NASA's history, and the initial repair rescue mission for the Hubble Space Telescope, which will be the subject of today's discussion. Dr. Hoffman has also been a member of the faculty for the International Space University since 1994. The title for today's lecture will be The Hubble Space Telescope, What Went Wrong, How We Fixed It, and Its Great Discoveries. Please welcome Dr. Jeff Hoffman.
Thank you, Omar. All right, good evening, ladies and gentlemen. I hope everybody over here can see the screen. So, Hubble Space Telescope, I'm assuming it's been in the news a lot. Its fantastic pictures are still coming around. It's so well known. I think if you ask probably anybody in the world, name a telescope, if they can name any telescope, it would be the Hubble Space Telescope. But let's go back to the beginning. The Hubble telescope is up in orbit. Why? What's happened here? Don't know what happened there. In any case, why bother to put a telescope in orbit? We have lots of good telescopes on the ground. It's expensive to put something in orbit. Well, really, almost before the dawn of the space age, some far-thinking astronomers like Lyman Spitzer at Princeton and some other people understood that on the Earth, we're always looking through this. You can see this blue line here is the view that we have from space of the Earth's atmosphere. Telescopes on the ground have to look through that, and that gives various problems. First of all, the atmosphere blocks a lot of radiation that astronomers would like to study. Ultraviolet radiation, a lot of infrared radiation, X-rays. Very nice for us here on the Earth that it blocks them, because some of those radiation would not be very good for our health, but astronomers are very interested, and only by going up above the atmosphere can you observe all of the electromagnetic spectrum. Also, the atmosphere is constantly moving around, and so when you look at an image of a star through a telescope, it's always wiggling around. That limits the precision with which you can look at it. It limits the sharpness of your image. So the dream, even before the space shuttle was built, was someday to build a large, optically perfect telescope that could be put above the Earth's atmosphere and this was the dream, that it would give an unprecedented view of faraway galaxies, of things that we just could never have observed before. But that wasn't the only thing about the dream of the Hubble telescope. Great telescopes on Earth, the Palomar Observatory, for instance, the key part of any telescope is the mirror, which is here at the bottom of the telescope. Once you've built the mirror for a telescope, it's good for decades. You have to put instruments at the focus of a telescope to basically look at the pictures or to measure the spectra. And although the mirror is good for decades, the technology of the detectors that we use is constantly improving. It's just like your computer memory. Moore's law, it doubles every 2 years. The sensitivity and resolution of astronomical detectors has constantly been improving. On the ground, if you have a telescope, first of all, if something breaks, you just go and fix it. But even more important than that, as new detectors are developed, you can take out the old detectors and put the new ones in, and the telescope becomes more and more sensitive. We never had the ability to do that in space. Basically, you put a telescope up in a satellite, you launch it, and that's it. If something breaks, well, maybe you had some redundancy, in which case it can continue to work. But more importantly, if new detectors are developed on the ground, well, that's too bad. The satellite is up in space. Maybe you can launch a new satellite, but that's going to be a whole new rocket launch, expensive. So the dream of the Hubble telescope was to take an optically perfect mirror, and this is actually the mirror that's in the Hubble telescope before it was loaded in. This is a mirror that is, in order to be optically perfect, this mirror had to be flat to within a fraction of the wavelength of light, just to give you a sense of what that challenge was. If this telescope mirror were the size of the North American continent, about 5,000 kilometers in diameter, the largest ripple on its surface couldn't be more than a few centimeters. That's how flat it had to be. It was a tremendous technological challenge, and yet it was done. But as I said, that wasn't the only challenge. It was the concept that we could actually make a telescope that would be put into space and could be serviced by space-suited astronauts working out of the space shuttle was a tremendous leap of faith, because the Hubble telescope was conceived and they started building it before the shuttle had ever flown. But that was the dream, that we would have this optically perfect telescope, and through servicing, we could continually upgrade it to keep it on the forefront of astronomical instrumentation. Now, I want to say in advance that I'm going to go, some of the stuff I'm going to be talking about is a little bit technical. We have a lot of International Space University students here, but bear with me. There's a lot of cool space stuff as well if I lose some of the people. Because this is one of the things that I wanted to show you is, this is what we were expecting to get from the telescope. This resolution in terms of arc seconds, these are the wavelengths. And for you ISU students, you know about diffraction, and that the shorter the wavelength, the better your resolution. So in the visible range, you could get about a 20th of an arc second of resolution. This is what we were hoping to get from Hubble. So how do you make a great telescope mirror? The Hubble Space Telescope basically took the telescope technology of the mid-20th century, just like the great Palomar mirror. You start out with a huge chunk of glass, which you see here. There's a hole in the middle, and I'll show you why in a minute. And then you polish it to make it just the right shape to be able to focus the light. Now, the easiest shape to make in a mirror is a sphere. I don't think we have too many amateur telescope makers who make their own telescopes anymore, but back when I was a kid, a lot of people did that. And actually, there are a lot of tests that you can do with a spherical mirror. Kind of interference tests, you get these very sharp lines, and that shows you that your mirror has a perfect spherical shape. Well, the problem with a spherical mirror is this up top is a spherical mirror. And the problem is that the light that hits the outside of the mirror is focused at a different place than the light that hits the inside of the mirror, and that's called spherical aberration. Remember that word because it becomes critical in the history of the Hubble telescope. So what you have to do in order to get all the light focused at just the right place, and there's other types of aberration which I'm not going to go into, you have to actually make the mirror slightly flatter than a sphere. And then all of the light, no matter where it hits on the mirror, and no matter which direction it's coming from, it's all focused at the same place. Once you've got the mirror, then this is the optical configuration. Essentially, the light bounces off the primary mirror, and this mirror is about 2.4 meters in diameter. It is reflected off a secondary mirror, and then it goes through that hole. You remember that you saw the hole in the middle of the mirror, and it all comes to a focus behind the primary mirror. And this is the overall configuration. Behind the primary mirror is where you put the optical instruments. And Hubble has about 5 different detectors, and then they also have some star sensors which help it point in the right direction. So that's the basic way that Hubble is constructed. In the picture of Hubble then, the mirror is kind of up around here. This is the open section, the secondary mirror is up front, and then all of the detector instruments are in the back. Now, making a telescope, first of all, is optically perfect like this, that can be launched into space. It has to be perfectly thermally controlled so that when it's going around the Earth every 95 minutes, getting hot, getting cold. You have to have a thermal structure so that it doesn't expand and contract and change the focus. Also, you have to design it so that astronauts can go in and pull out old instruments and put in new instruments. All of this was new technology which had never been done before. So it's not surprising, as with many advanced space projects, it was over budget, it was behind schedule. People don't remember this now, but even before Hubble was launched, there was a lot of criticism that, this is a telescope it's never going to get launched, it's too expensive, and so on and so forth. But in fact, in the spring of 1990, it was taken into space by the Space Shuttle Discovery, put into orbit. There was a lot of excitement about it, a lot of publicity, and to the, I think, satisfaction of not only NASA, but the whole astronomy community, the general public really picked up on it, the idea that Hubble was going to be able to unlock the secrets of the universe. People are really excited about that. And so, many of the young people in the audience weren't even born when this happened, but those of us who are old enough remember what a disaster it was when the first images started coming back from the Hubble telescope, and to their horror, the astronomers discovered you couldn't focus properly. When you pick up a pair of binoculars, what do? You hold them up to your eyes, you take the focus ring, you go back and forth, and you try to find the sweet spot in the middle where everything is in focus. And that's what you do with the new telescope, and that's what they did with Hubble. And this is the best that it could do. It was an absolute disaster. Instead of a star being a single point of light, the image was smeared over a much larger area. So all of the dreams that people had for Hubble were falling in ashes. It was an absolute disaster for NASA, for the astronomy community, headlines all over the world. The Hubble telescope was a joke for late-night comedians. It was denounced in the halls of the US Congress as a techno-turkey. It was a disaster for NASA. At the time, NASA was going to the US Congress, trying to convince Congress to start funding for what NASA wanted to start to build, what's now the International Space Station. Well, as you can imagine, NASA was not very popular in Congress. So they basically said, hey, go do something about Hubble and then talk to us about a space station. So, what do you do when you have a problem? Well, the first thing you have to do is to understand what the problem is. Here was basically the problem. This was the way the Hubble was designed, that this is the angular resolution. Within 1/10 of an arc second, you should have had over 80% of all the light, a really sharp image. Instead, the light was spread over a much wider area, and that's why all the images looked fuzzy. That was the problem. How did it happen? You have to understand that if we're going to fix it. Well, remember I told you when you're polishing a mirror, the easiest way to polish it and measure it is a sphere, but we can't. We have to make it slightly flatter. So how do you measure the shape? Well, as I said, it's easy to measure a sphere, but this was kind of a hyperbolic shape. And so in order to do the measurements of its shape, they actually install a miniature telescope on top of the mirror. Here's the actual mirror of the Hubble telescope. And this is not to scale, but they put another telescope on top of it, which essentially takes the hyperbolic shape of the Hubble mirror and transforms it into a spherical shape, which you can then measure. This instrument is called a hyperbolic null corrector. Now, in order for it to work properly, it's absolutely critical that it be positioned at just the right distance away from the focus of the main mirror. And so in order to do that, they have what we call a measuring rod, which is precisely positioned, and I'll show you the actual picture of how they put it, but that is essentially what is required if you're going to make the measurement of the right shape. So in order to be sure that that measuring rod is put at just the right position, they put an end cap on it. This is the end cap here, with a little hole in the middle. The top of the measuring rod was reflective, and then the idea is they would shine a laser down through that hole. It would reflect off the top of the measuring rod, and doing that, you could exactly measure the proper position of the measuring rod. This is a picture of the measuring rod. You can see the end cap over on the left. And this is the installation. And you can see once it's installed in there, it's pretty hard to do anything with. So installing it properly is critical. After the fact, the investigating team spoke with the technician who installed it. And he said, well, you know, it didn't seem to go in properly. I had to use 3 shims to get it in the proper position. Man, that should have been a red flag that something was really wrong. And in fact, along the way, we've discovered in retrospect, there were many red flags which should have indicated to people that something was wrong. But he didn't tell anybody about it. He just installed the end cap. Now, the people who designed this measuring rod anticipated the possibility that it might be installed incorrectly. So in order to make sure that the light only was reflecting from the mirror, they wanted to be sure that the light didn't get reflected from the top of that end cap. So they put an anti-reflective coating on the top of the end cap. That way, only the measuring rod itself would reflect that light. Well, again, the investigating team went to the factory in Connecticut where the mirror was manufactured, and they found this measuring rod and the end cap. It was stored away in a closet. Sometimes you're just not lucky. A little bit of this anti-reflective coating had peeled off right from around that hole. And so, exactly what people had tried to prevent is exactly what happened. Instead of the light reflecting off the top of the end cap, of the measuring rod, it reflected off the top of the end cap, as a result of which the measuring rod was positioned about 1.3 millimeters away from its proper position, which doesn't seem like a lot. But given the precision of the Hubble optics, that meant that slightly too much glass, the mirror was made slightly too flat. A little bit too much glass was removed from the outer part of the mirror. How much? About 2 microns. An average human hair is about 50 microns, so 1/25th of the diameter of a human hair. That's how much too flat the Hubble mirror was. But it made all the difference. And so, in the end, the Hubble telescope did have spherical aberration, and the light that was hitting one part of the mirror was not focused at the same place as the light that was hitting the other part of the mirror. Once they understood what the problem was, then you could do a computer simulation, which you see on the bottom, saying, you know, if the measuring rod was 1.3 millimeters off, what would the images look like? And sure enough, it looked remarkably like the upper images, which is what Hubble was actually doing. So all right, we now understood what the problem was. The mirror was slightly too flat, and we understood how that happened. What are you going to do about it? Well, remember, this is the optics of the telescope. There were all sorts of crazy ideas. There was a committee of astronomers, optical engineers, astronauts. Remember, whatever was going to be done had to be done in space by spacesuited astronauts. There was some idea of maybe they should bring the telescope back to the ground and fix it, but people were worried about contamination and the expense. Maybe it would never get launched again. We really wanted to fix it in space. So here's what people finally came up with. Coming through the mirror, you've got this out-of-focus beam, which every instrument, every detecting instrument, shared that beam. They had a little mirror which would stick out, reflect the beam into the instrument. So what we had to do, somehow, for every science instrument, we had to put in 2 tiny mirrors, each of them about the size of your thumbnail. The first mirror would intercept the out-of-focus light, which you can see that M1 mirror there, bounce it off another mirror, which was slightly curved, just to compensate for the lack of curvature in the primary mirror, and then that light, which would now be in focus, would be put into the science instrument. Now, it turned out that NASA had always been planning to have a servicing mission in December of 1993. One of the primary observing instruments, the wide field camera, was not working well. It was not sensitive in ultraviolet light. Another, the so-called wide field camera 2, was being manufactured at the Jet Propulsion Laboratory. And so we were actually able to put these corrective mirrors inside. And that's a picture of me holding this wide field, the new wide field camera. And so that camera had the corrective optics built in, and all we had to do was take out the old one, put the new one in, which is what Hubble was always designed for. It's a very delicate operation, but we knew what we were doing. But there were 4 other detector instruments in the telescope. We didn't have any replacements for them. What are we going to do to rescue them and make them useful? Well, all of those detecting instruments were enclosed in compartments about the size of old-fashioned telephone booths, big enough for a person to get into. It was a very, very critical job designed by optical and mechanical engineers. You had to have lots of mirrors, but the problem was the mirrors couldn't all be deployed. They all had to be sort of folded up inside that telephone booth size enclosure. Then we would have to remove one of the instruments from Hubble. It would be sacrificed. So we took out the instrument which had the least use. We would put in this big box, and then all of the mirrors this is kind of a schematic, the mirrors would be deployed by motor drives, and they would all sort of spread out like the skeleton of an umbrella, and they had to be put into exactly the right place. I mean, this was a very complex job. This is a schematic, a little more precise schematic of one of the configurations for the Goddard high-resolution spectrograph, but all of the instruments in there had to have these sets of mirrors, all of which had to deploy. And this particular set of mirrors, what I should do looking ahead, because hopefully you recognize that we were on the first servicing and rescue mission, but there have been a series of 4 subsequent missions. We've serviced Hubble 5 times, and each time we go up, when we put in a new instrument, the corrective optics are built into it. And when the last servicing mission went up in 2009, the last of the old instruments was removed, so they no longer needed these special mirrors that we put in. And here you can see this is the corrective optics package that we were actually in the process of installing. All of the mirrors are folded up, and they'll eventually come out of this little hole in here. But that was brought back to Earth on the final servicing mission, and these are some of those little mirrors. It's in the Air and Space Museum in the Smithsonian in Washington, D.C. Give you some idea of the complexity of what had to be manufactured. So, okay, we understood what went wrong with Hubble. We had a plan to fix it. Now, for all of us in the astronaut office, the big question was, who's going to be on the crew? As you can imagine, this was a primo mission that lots of people wanted to be on. It was also the most critical mission that NASA was going to be conducting with a space shuttle. The stakes were really high. So everything was done to reduce the risk of failure, including the decision that only crew who had previously done a spacewalk would be eligible to be selected to do a spacewalk on the Hubble mission. This is where sometimes luck plays a role in your career, because I'm going to go back to my first mission in 1985. God, I look young there. I love it. We went up on what was considered to be a standard shuttle mission at the time, to take up 2 satellites, deploy them, stay up for 4 days, and come back home. Well, the first one went up just fine. There's a motor on the bottom here, which we take it up a few hundred kilometers, and then that motor takes it up to geostationary orbit. This one was a Canadian telecommunications satellite. This was a communications satellite for the US Navy, which we deployed on the second day. And we looked at it. We'd done this many, many times in the simulators, and about 2 minutes after you deploy it, there's a little antenna here which pops up. And we had seen this, as I say, many times in the simulator. Well, we looked, and after about 5 minutes, I realized, the antenna didn't pop up. And so we called down to the ground, is something wrong? And it appeared that the satellite had not turned on. There is a little switch on the satellite. Now, what the people on the ground started doing was there anything that we could do about this? We were up there. The satellite was already in orbit. We didn't have any special equipment. Were there any what we call single point failures? The failure of one single thing is the most likely cause of any failure. Well, there was a little switch. You can see it here on the outside. When that satellite is inside the shuttle, that switch is held closed. It's part of the ignition circuit that turns on the satellite. You do not want the rocket motor firing when it's inside the shuttle. That would be a bad day. So that's one of the many safety features. And so the thought was, maybe the little micro switches underneath that have jammed, and could we somehow go out and wiggle that switch a few times and maybe activate the satellite? So we went into full gear. If you've ever seen the Apollo 13 movie when they dumped all the equipment on the table and they said, all right, make this special tool that you can convert from one scrubber to another, that was sort of what they did here. You know, they dumped everything that we had on board onto the table, and the people, the engineers on the ground, were charged, you know, make a tool that they can use to go out and wiggle that shuttle. And so so here we are, Ray Seddon is, you know, we took the cover off one of our checklists, and I mean, just all sorts of things. We were also going to have to do a rendezvous with the shuttle. We actually, in this flight, I had been originally assigned to fly in June of 1984. That flight got canceled. We were reassigned to fly on a flight in August of '84 where there was going to be a rendezvous. So we actually had about 3 months of rendezvous training. But then that flight got canceled. We were assigned to fly on another flight in January of 1985, and we actually got into pre-launch quarantine on that flight, and then it got canceled. These things happened in the early days of the shuttle. And so we finally ended up on a flight in April of 1985 with this satellite. You know, what were the chances of that? And the idea was we would make these tools, and then on every shuttle mission, even if you're not planning to do a spacewalk, 2 of the crew are trained on how to do a spacewalk just in case something goes wrong. I was one of those 2 crew, and so there we were, all of a sudden doing what had never been done in NASA's history before, to go out on a contingency, unplanned spacewalk to do something that had never been planned before. And our job was to go out and take those tools and attach them to the end of the robotic arm. We didn't have any special equipment. We didn't have any foot restraints. So what we actually had to do was to wrap those around. You can see the wrapping material here. I'm going to, this little strap there. Of course, when you're working and you don't have any foot restraints, you have to hold on with one hand, otherwise you'll go unstable. So everything you do, you can only use one hand. So the 2 of us, each using one hand, we had to hold those 2 tools in place, which, by the way, look kind of like fly swatters. So we became known as the SWAT team. Some of you will get the idea there. Try sometime working with a partner, each of you use one hand and try to tie your shoelaces, and you'll get some idea of why it took us almost an hour to get that job done. But we did it. And then the next day, we actually did a rendezvous. We didn't have a rendezvous list with us. They had to send the whole checklist up on a teleprinter. And I mean, it was really quite extraordinary. And anyway, the bottom line was I had done a spacewalk, so I had my EVA Spacewalkers Union card, and I was fortunate enough then to get selected to be on the crew that was going to go up and rescue Hubble. 4 of us were going to do spacewalks. The other unique thing about this flight, there were not only the optical problems on Hubble, there were about a dozen different things that had gone wrong. The solar arrays didn't work properly. Every time they went from night to day, they started vibrating. One of the tape recorders had failed. Circuit breakers had broken. There were a lot of things we had to fix. We had to schedule 5 different spacewalks, which had never been done before on any NASA mission, even back in Apollo. And so we had 2 teams of spacewalkers. My partner and I went out on days 1, 3, and 5, and Tom Akers and Kathy Thornton went out on days 2 and 4. Tremendous amount of training, using the manipulator arm, both for capturing Hubble and for moving the astronauts around during the spacewalks. Very critical. For us spacewalkers, we spent about 400 hours working underwater, which is where we do most of our training. The reason you work underwater is because, well, if I were standing here in a spacesuit weighs about 300 pounds, so what, 130 kilos or so. You really can't do anything on the ground. But in the water, the spacesuit is filled with air. It wants to float up to the surface, and so then you put lead weights on your chest, on your arms, and your legs to make yourself neutrally buoyant so you don't float, you don't sink. And it's remarkably like the experience of being in space. In fact, of course, I had spent quite a bit of time in the water before my first flight, even though we weren't planning to do a spacewalk. And I remember the feeling when I opened the hatch and first went out, and I was facing down towards the shuttle, and I had to sort of move over to the tool chest to get the tools we were going to use. And the thing that was going through my mind was, you know, this really feels a lot like being in the water. Then, of course, I turned around, and there was the earth and the sky, and it's like in The Wizard of Oz. You know, Toto, we're not in Kansas anymore. We definitely were not in the water tank. For the first time, we introduced virtual reality as a training tool. We would plan a lot of the activities even before we went in the water tank, so we knew exactly what position we wanted to be at. The critical thing in doing a spacewalks for Hubble was the limited amount of time we had and the large number of tasks. So you can't afford to waste time, and we had to make sure that everything we did was as efficient as possible. Here's a picture. You saw the picture of me holding this wide field camera. Here we are over and over again. We practice. We had to be, you know, what position should Story have his foot restraints so his arm could grab it and help guide it in? Remember, there's critical optics in here. You don't want to bang it and mess up anything. None of us wanted to be known as the astronaut who broke something on Hubble that wasn't already broken. So quality control and making sure that we didn't make any mistakes was absolutely critical. Of course, the actual instrument is much more complicated than this, so we also spent a lot of time in the clean room up at the Goddard Space Flight Center working with the real instruments so that we got to know what they really looked like. After over a year of training, we get in our T-38 training jets, fly down to Cape Canaveral. There's the shuttle on the launch pad. It's always an exciting moment. At this point, we're in medical quarantine for a week. The night before launch, everything is lit up on the launch pad. It's an exciting time, and of course, not nearly as exciting as when they light the rocket and 4.5 million pounds is on its way up into space. I'm going to show you now a sequence of slides which will explain how you get ready to do a spacewalk, and then I'll show you a short video of what we actually did. So all of the spacesuits, and instead of the normal 2, of course, we had 4, and they're all packed up in the airlock. So the first thing we have to do is unpack everything. You can see it's pretty crowded in there. All of the delicate equipment is packed in these foam boxes to protect it against launch vibration. Tools were absolutely critical. We had about 200 different tools to use in the repair, about 100 of which we were actually planning to use, and the rest of them were for contingencies. A spacesuit is like a miniature spacecraft. Your life depends on it. It's got to provide you with pressure, with oxygen, with thermal control, with communication. So we take our spacesuit checkouts very, very seriously. You don't want to go out when you don't have full confidence that your spacesuit isn't operating. Here in the back of the spacesuit backpack, there's both the battery, which runs all the electrical equipment, and the carbon dioxide scrubber. The spacesuit has an atmosphere of pure oxygen at about 0.3 of an atmosphere, and we rebreathe this same oxygen over and over again. But of course, we exhale carbon dioxide, so you have to remove that in order to be able to continue to use the same oxygen. On the morning of a spacewalk, I'll get up early, have a bigger breakfast as I can, because I know I'm not going to get anything to eat for about 8 hours. You can see we have some radiation monitors on us there. Hubble was at an altitude of about 600 kilometers, which is as high as the shuttle could go. They wanted it up as far above as much of the atmosphere as possible to avoid problems with the pointing system. So we knew that we were going to be brushing the inner parts of the Van Allen radiation belt. We were going to get about 10 times the normal shuttle radiation dose, which is nothing dangerous, but they wanted to monitor our dosage. So we had those radiation monitors. We also put on a heart monitor, which the flight surgeons like to see. 2 sets of underwear. The inner underwear is thermal underwear, sort of like you wear if you're going to go out skiing, although because the spacesuit has a pure oxygen environment, it has to be made out of fire-resistant Nomex. That'll keep you warm. The outer set of long underwear has many, many meters of Tygon plastic tubing through which you circulate cold water, because when you're in the sunlight, it can get very, very hot. And that way you can adjust how much cooling you want. Then once you're in your underwear, you get into the lower part of the spacesuit. And of course, in space, you can put your trousers on 2 legs at a time. You just float in there. Then you float into the airlock where the upper part of the spacesuit is hanging on the wall. The yellow material you see there, those are the arms with the shoulder bearing joint. And that yellow material essentially is the impermeable material that holds the gas inside. It's a really tight fit. You can see I'm pushing and squeezing to get myself in, and it's a good feeling when you finally get inside. Now, as I said, we run the spacesuit at 0.3 of an atmosphere. The reason we want it at a relatively low pressure is because you can think of a spacesuit as an anthropomorphic balloon. And if you've ever blown up those long, thin party balloons, you know that if you try to bend them, they snap back. Because when you bend them, you're compressing the gas inside. Same thing with a spacesuit. When you bend your arm, you're compressing gas. And the lower the pressure in the spacesuit, the more mobility you have. So we want to keep the pressure low. That's why we use pure oxygen. We don't waste any of the pressure on nitrogen, which for a short term at least, you don't need. Problem is, if you go from 1 atmosphere to 0.3 of an atmosphere, you'll get the bends, decompression sickness. Nitrogen will bubble out of your blood, just like a scuba diver who comes up too fast. So what we do here is, after we get in the spacesuit, we purge them with oxygen for about 10 minutes, get all the nitrogen out of it, and then we breathe pure oxygen for about 40 minutes. And that gets enough nitrogen out of our system that we can depressurize without the danger of decompression sickness. So now let's look at a video of what actually happened when we went out. And of course, I'm not telling this as a suspense story. You know that we did fix it, right? It really did work. But it's a great story, and it's nice to share it with you. So that's our crew patch. That's our launch. We launched at about 4 a.m. in the morning. A lot of them, night launches are spectacular. It's really like a second artificial sunrise, lighting up the entire Florida beach. And I have to tell you, it's pretty spectacular on the inside. This is what the Earth looks like from 600 kilometers. Every day in space is a bad hair day. Kathy showed that. Getting our tools ready, the Hubble optics are susceptible to organic contaminants, which is why we're wearing plastic gloves. The first job for the pilots were to basically rendezvous with Hubble. So we periodically fire our engines, gradually approach. Really exciting. You know, first you see it as a point of light and it gets bigger and bigger. And it really is big. It's about 15 meters from top to bottom. Our arm operator, Claude Nicollier, a Swiss astronaut, grabbed it. We put it down. We latch it into the shuttle. And now we're ready to go to work on the first of the 5 spacesuits. So here we are with our radiation monitors, putting on the heart monitor, in our spacesuits, finishing our pre-breathe, ready to go. And there's that magic moment when I was the first one out the airlock, ready to go. Now, actually, as I said, there were many things wrong with Hubble, including the rate gyroscopes. There are 6 of them, and 4 of them had broken. And so actually our first job was to open these big doors and replace those gyroscopes. In order to do that, Story had to actually slide underneath. I'm using the power tool there to undo the bolts. Then he would lift out the old gyro, hand it to me. I'd hand him one of the new ones. He'd put it in place. I'd put the bolts back in. And then very delicately, we have to slide him out. As I say, we don't want to break anything, and you don't have a whole lot of visibility when you're in the spacesuit. You can't see what's behind you. So we had to sort of guide each other, and I'm sort of manhandling him just like a package. Everything worked fine until I actually went to close the doors. Here and you can tell it's me because of the red stripe there. I'm putting that gyroscope back into the old gyroscope into the thermal container. Keeping everything at the right temperature is very critical, which is why we have these big boxes with a lot of insulation on them. And you can see how important it is. My feet are in a foot restraint, and Claude is moving me around on the arm, which makes for a lot more efficient spacewalking than if I had to just go hand over hand, especially when you're trying to carry something and move it with you. Then I went back to close the doors, and really it was a big shock. The doors would not close properly. They were warped thermally. And this was the very first task that we went out to do. If you can't close the doors, you've lost the telescope. So this took us about an extra hour, over an hour, before we could figure out what the problem was, and we had to then figure out, it took both of us to get it, and we had to make special use of a different kind of a tool, and we finally did get the doors closed. And a good example of how having people up there, we could actually analyze the problem and solve it. Rolling up the Hubble telescope, solar panels like an old-fashioned window shade, and we were going to remove those and bring them home and replace them with new ones. Unfortunately, one of them didn't roll up properly, and you can see why. The stiffening rod had been warped, probably because of thermal stress. So when Tom and Kathy were getting ready to go out the next day, they knew that we couldn't bring that one home. Kathy would have to attach a handhold to it. Tom would release it from the telescope. Claude would move Kathy, the solar array, with the arm over to a position as far away from the shuttle as possible, and she would let go of it, and we just have to basically leave it overboard, and eventually it would deorbit. So now she lets go of it. Now, of course, the solar array does not have any propulsion of its own, so we have to move away from it using the shuttle maneuvering rockets. And you'll see in a minute when the exhaust from the maneuvering rocket hits the solar array, and it starts to move. It's sort of like the wings of a prehistoric bird flapping. And you can imagine when you're flying up to the International Space Station with those big panels up there, you have to use special techniques to make sure that you don't damage the solar panels. That's one of the new solar panels. We installed it. These things weigh hundreds of pounds on the Earth, but you don't have to be an Olympic athlete to move them around because they don't weigh anything. They do, on the other hand, have inertia, which is why you see us moving very slowly. In fact, a lot of these pictures are speeded up by 2 or 3 times, otherwise it would just be impossible to look at. So getting ready for the third spacewalk, here we actually are removing the wide field camera, which could not focus, and here I'm taking it out. Again, this day I was riding on the arm. We put it in storage over on the right side, and now we're taking out the new one out of its thermal container. Again, moving very slowly. And there, you can see on the bottom is that mirror. Remember I told you each experiment has a mirror which goes into the light beam. That mirror is protected by that little cage which we had to remove, and now we install it And this was a very good feeling for all the astronomers on the ground, because with that installed, at least we had one working, we hoped, one good working instrument in the Hubble telescope. And now we put the old one away, and we closed the container, and we brought that home. And for a while, it was on display in the Smithsonian Air and Space Museum. So that, particularly, all of my old astronomer friends breathed a sigh of relief. A lot of them had called me before the flight asking, "Hey, Jeff, can you guys really do this?" And of course, we hoped we could, but when you actually get it done, it's a good feeling. We then went up to the very top of the telescope. We had to install 2 new magnetometers. The magnetometers are relatively simple instruments, and they were not designed to be replaced. They should never have failed, but they both failed, and so we had to put in new ones. Now here comes Kathy holding on to this corrective optics package you can see inside. Now, she can't see what she's doing, and so Tom actually has to get inside the telescope. And again, remember, there's a lot of critical stuff in there, and there's not a whole lot of clearance. Oh boy. But again, it did work successfully. This is an example of how we use the power tools. It really saves a lot of time and wear and tear on your wrists. Look at all the tools that are hanging from the tool carrier on their chests. Here's Kathy coming into the airlock. Every single tool has to be tethered. You don't want your tools floating away if you let go of them. After every spacewalk, you have to clean out the suits, disinfect them. By the way, there's nobody in that suit. Astronauts are flexible, but not quite that flexible. And then get the next set of suits ready. When we were replacing the magnetometer, I saw some peeling paint, and they were worried about contamination. So this was an unplanned task where we had to make some special covers. And so the fifth and last day, and this day I was the free floater, and Story was attached to the arm. And we went way up to the top again to put on those covers. What an incredible workplace. I mean, there we are, 400 miles, 600 kilometers above the ground. The motor to deploy the solar panel didn't work, so it was nice that we were out there because we put it down manually. And then we actually stayed out while all of the rest of the equipment was deployed to get the telescope ready to put back into space. That's the new solar panel. They have insulating material on the outside of the stiffening rods, and that deployed properly. You can see me over at the left just sort of hanging out, waiting for all of that equipment to be deployed. And so there at the end of the 5th and final spacewalk, on what many people had considered was a mission which was too complex, where NASA had maybe bitten off more than we could chew, so to speak. But we had done everything that had been set out for us, and we were understandably both relieved as well as extremely happy. And there is the brand new Hubble Space Telescope ready to be put into space. Now all we had to do was to put it back into orbit, which was the job of Claude, and I don't know why it stopped here. Oh well, I'm going to go on to the next one. So I took a few pictures while I was out there just to share with people what it looks like to be out working with the Hubble Space Telescope. You can see the old wide field cameras still out there. We had just installed the new one, and we had to wait for just a couple of minutes while the ground did a checkout to make sure that all the connections were properly attached. If they weren't, we'd have had to go back and fix them. So that gave me just a few minutes to snap these pictures. And that's what it looks like when you're out with the Hubble telescope, and you can see Story, my partner, over on the other side. It's a very wide-angle lens, so there's a lot of optical distortion. The Earth is not flat, take my word for it, okay? We went around it every 95 minutes. But what a spectacular working place. I like this picture. It's the transparent Hubble telescope. Look, you can see the Earth right through it. And I'll leave that as an exercise for the students. And every once in a while, it's just so beautiful. The sun rises and you just have to sort of, whatever you're doing, you just kind of stop and watch the sunrise, or maybe it's the sunset 15 times a day. Most orbits, by the way, are 90 minutes, and you see 16 sunsets a day, but because Hubble was in a higher orbit, and all of you students are going to study your orbital mechanics, so the orbit takes a little bit longer. Just a thing. This is the perspective that we had. As I said, it's 15 meters from top to bottom, and it looks, when you're at the bottom of it, it really looks big. And this is the magic moment, just hanging on. Of course, we're both attached by stainless steel wires, but the wires aren't pulling on us. And I'm enough of a physicist, I understand orbital mechanics. I know that if I let go, I'm not going to go anywhere. I mean, there's no wind, and we're both moving at 8 kilometers a second. So every once in a while, I would just let go. And what was amazing, it was not just that I let go, it was like a physical, psychological transformation. When you're holding on, the shuttle is so massive that you push and you pull, and you're basically part of the shuttle system. When I let go, all of a sudden, I was a free-floating satellite. You know, obviously I was flying along with the shuttle, but there was this incredible psychological transformation, which I'll never forget. Not a place if you suffer from vertigo. It's a long way down, and there have been some EVA astronauts who have reported senses of vertigo. In addition to closing the doors, we had one other potentially serious problem, which I'll just tell you about briefly. On the last day, we had to replace an electronic unit that controlled the solar panels. This was a unit which was not planned to be repaired by astronauts. So instead of having big bolts that were easy to work with, if any of you remember the old SCSI connectors on computers with the little 2mm screws on them, we had about 16 of those that we had to remove and change the connectors. And the screws were supposed to be captive, but they weren't, and so they started floating around. We had a trash bag, and we would try to grab the screws, put them in the trash bag, but as the trash bag got fuller, you'd open it up to put one screw in, and 2 screws would float out. They've since redesigned the trash bag, by the way. And at one point, Story, who was locked onto the end of the arm, he grabbed for a screw, didn't quite get it, and it started floating down towards the cargo bay. You don't want spare metal getting caught in the mechanisms of the cargo bay. You know, maybe it'll stop you from closing the doors. So I was free-floating, and I lunged out to try to get it, but it was just a little bit too far. And I was holding on to the arm. I didn't want to lunge out into free space because that could have been dangerous. So then Claude, who was operating the arm, said, well, hold on, Jeff, I'll move the arm and you can get it. Well, it turned out that the maximum speed that the arm could move was the same speed that the screw was moving. So I was holding on and the screw was out there and we were both moving. And again, here's where the training comes in, because it turns out that when anything is on the end of the arm, whether it's an astronaut or a satellite, the arm is programmed to limit the speed at which it can move. So our pilot, who was the backup arm operator, knew this. He quickly floated over to the computer, changed the parameter to tell the arm that it's unloaded, and all of a sudden the arm sped up and I could grab the screw, and that was the great screw chase, and we won. We got the prize. So, as I said, we knew that we had done everything that was set up. We had done our job. Hubble had been repaired. But would the optics actually work? Again, this is not a suspense story. You know that it did, but we didn't know at the time. And the thing is, you can't turn on the instruments right away. You have to give them about 2 weeks to outgas. Otherwise, when you turn on the high voltage, you'll get sparks and you'll blow your electronics. So it really wasn't until New Year's. It was, and I'll never forget this moment. It was New Year's Eve. We had a party. It's about 1 o'clock in the morning. I was cleaning up the kitchen. The phone rang. It was an old astronomer friend from the Space Telescope Science Institute. After, Happy New Year, Jeff, Happy New Year. Do you have any champagne, Jeff? Well, yeah, we had a half a bottle still in the refrigerator. He said, well, pour yourself a glass. I'm not supposed to tell anybody this because one of our politicians wants to make an announcement in a few days. But we figured somebody on the crew should know that we've got the first images back from Hubble, and it worked, as you all know. Hey, it's not a suspense story. You knew this, but it's great. I mean, it really was, it was like the voyage of the damned into heaven, from just NASA's worst disaster. Hubble has turned into the most successful science mission, most productive mission that NASA has ever had. And I just want to spend the end of the talk reminding you of the incredible things that Hubble has done for us. This iconic picture of the birth of stars, and it was celebrated on the 25th anniversary of Hubble. I still get goosebumps when I look. It's biblical. I mean, let there be light. Stars are being born here. And we see stars dying, these incredible planetary nebula when the stars shoot out their atmospheres. I mean, it looks like the work of a psychedelic artist, but that's our universe. Those things are there. They really exist, and Hubble has been able to share these, and this has been the incredible thing. You can go on the web and download Hubble Heritage pictures, and anybody anywhere in the world can do this for free. The other thing that I want to leave you with is to remind you that we were only the first servicing mission. There have been 4 more. Not only have they fixed things that have subsequently broken on Hubble, but every time they went up, they installed new, more powerful, more sensitive instruments. On the second mission, and I was actually the EVA Capcom for this, they actually found that some of the insulation on Hubble was peeling. So again, they went into rescue mode, and we figured out on the ground how they could make new insulation, and since then every crew has gone up and fixed Hubble insulation. The third mission, actually this mission was split into 2 because the gyroscopes that we had put in failed again. They've been a high failure point because they spin about 9 billion times every year. I mean, it's a high failure mode. And the gyros had broken again, and the telescope was actually not working, so they wanted to get these people up as soon as possible. You notice the dates there. It was supposed to be a longer mission, but everybody remember Y2K, how every computer in the world was supposed to go belly up. They didn't want the shuttle flying at the end of the millennium when Y2K happened, so they had to bring them home early. And they finished the rest of the repair on what they called the 3B mission, where I have to say, those beautiful solar arrays that we put on, better arrays had been deployed. I mean, and they actually do work better, but they're not really nearly as pretty as the ones we put on, but there they are. So they took ours off and they brought them back. And every mission, the crew has been able to undertake more and more complicated tasks. So in this case, the main power distribution unit was showing signs that it might be getting old. To replace this, they had to completely power down Hubble. And that means you have no thermal control. There was about over 50 connectors which had to be removed from the old one. You put in the new one, you have to connect all of them. And if they hadn't been able to get that done properly, again, we would have lost the telescope. But with every successful mission, we're willing to take on more and more complex tasks, and sure enough, it worked. And as I said before, every time we go up, we put in yet another more powerful, more sensitive instrument and increase the scientific productivity. So that was Hubble after the 3B, which was actually the fourth servicing mission. Then a few years went by, and Hubble was getting old at this time. The batteries were nearing their end of the life, the gyros were failing again, and we were getting ready for the fifth and final servicing mission when we had the Columbia disaster. And if you remember, at this point, with the exception of Hubble and the Columbia mission, every other mission was going up to the International Space Station. The then administrator of NASA, Sean O'Keefe, decided it was too dangerous to do, and even once we fixed the problem of the foam coming off the external tank, had Columbia been on a mission to the space station, they would have seen that the wing was penetrated and they would have known that they couldn't come back. But the Columbia crew, they had no arm on board, and even if they had, they wouldn't have been able to have the right view, and they had no ability to fix it in any case. So had they been at the space station, at least they could have gone in for safe haven. And so the administrator decided there would be no more shuttle missions except to the space station, and we're going to let Hubble die. There was a huge public outcry. When Mike Griffin took over as the new administrator, he changed this. But in order to do that, we had to develop certain new capabilities. We put an extension on the robotic arm to make it twice as long, so that with a camera on the end, the crew could now do an inspection on their own right when they got up into space to check the entire thermal protection system to see if there was any problem. We also developed the capability of making at least limited repairs to some of the tiles. And finally, if it turned out that they got up there and they couldn't come home and they weren't at the space station, we were going to have two shuttles on the launch pad, a shuttle with a trained crew ready to do a rescue mission. And we had a crew that actually prepared for this. And so sure enough, we did this final servicing mission, and it was incredible success. They did replace the batteries. They put in the new rate gyro assemblies, basically left Hubble as good as new. New fine guidance sensors. I'm not going to read all of this. I just want you to get a sense. And this spectacular new spectrograph, which is many, many times more sensitive than Hubble was when it was first put in orbit. And as I said, every time we went up, we did things which we never would have dared doing before. One of the older spectroscopes, the power supply had failed a couple of years before. We didn't have a replacement for it, but we did have a new electronics board. Now, nobody, when Hubble was designed, ever imagined that we would be actually opening up an instrument, pulling out an electronics board and putting it in. But they figured out how to do it safely, and so that spectroscope is now working. And finally, someday, Hubble is going to have to be deorbited. It's big enough, it has no propulsion of its own. It's big enough that it's not going to burn up completely in the atmosphere. You don't want it to fall randomly over a city. And so someday we'll have to send up a robotic spacecraft which will be able to grab onto that capture mechanism, and you see an artist's conception here, and bring Hubble back. So that basically is the story of Hubble, and our servicing mission was only the beginning. It was the rescue, it was maybe the most dramatic, but it's been through the continual servicing. And just again, very quickly, this shows some of the great discoveries that have been made after each of the servicing missions. And again, for time, I'm not going to go through the details, but the idea should be clear that through servicing, we have kept Hubble on the cutting edge of astronomy. And the sensitivity that Hubble has now is almost 1,000 times greater than it had when it was launched, even if it had been launched with perfect optics. I mean, just the instruments. And so this is why when you look at the scientific productivity in terms of papers published, PhD theses, Hubble is so much more productive because every time we visit it, it's like putting up a new telescope. So, and this is the value of servicing, which is the message that I really want to leave you with. And finally, I just want to share with you, people say, well, what are my favorite discoveries from Hubble? So just a couple. I mean, there are so many. But the discovery of new planets around other stars has been one of the most exciting aspects of astronomy. In general, they're discovered either by dynamics or by eclipses, but Hubble actually has been able to photograph a planet moving around this star. You can see over the years. There's the planet now, but over the years we could actually see it move. Incredible, the precision with which Hubble can do this sort of operation. Seeing the birth and evolution of galaxies. Hubble is sensitive now that we can look back in time, because the further away you look, you're looking at the universe when it was much younger. And we've seen galaxies in earlier stages of formation, how they gradually get their spiral evolution. The new spectroscope that was installed, you see that little rainbow thing, that's the Doppler shift of a star going around a black hole in the center of a galaxy. Half of them are moving towards you and are blue shifted, half of them are moving away and are red shifted. And Hubble has been able to confirm that at the center of basically every galaxy, there is a huge black hole, including the center of our own galaxy. Einstein showed that mass can actually bend light waves. So if you have a distant object like a quasar out here, and you have a galaxy or a group of galaxies in the middle, the light can actually get focused for us here on Earth. And so when you look at this object, what you actually see is what they call an Einstein ring. That blue ring around is actually a very distorted image of a single object. And by studying the structure of that, you can actually measure the distribution of mass of the nearby galaxy or group of galaxies, and that confirmed what astronomers have suspected for about 50 years, that there's about 5 times as much matter in galaxies as we can actually see. This is the so-called dark matter that you may have heard about. But the most spectacular thing, I think, was done by Bob Williams, who was the second director of the Hubble Space Telescope Science Institute. I know Bob well, and he's a great astronomer. He grew up loving the stars. He said every time he got a new telescope for Christmas, he would take it out in the backyard, he would put a camera on it, and he would expose it just to see, what can my new telescope see? Now he was the boss of the greatest telescope in the world. As the director of the Institute, he had at his disposal 10 days, which could be used for any, they basically give the director the discretion to assign this to observing tasks that maybe might not pass peer review because they were a little bit sketchy. Well, his sketchiest idea of all was that Bob decided to point Hubble for 10 days. That's incredible value of Hubble time at a very tiny section of the sky, which, as far as other telescopes were concerned, was empty. And what he saw is what has come to be known as the Hubble Deep Field. Now we've with more and more powerful instruments, we have the ultra deep field, then we had the very deep field, now we have the ultra deep field. Almost everything you see here is a galaxy. In that tiny piece of sky, which is what you would see if you look through a soda straw, there are thousands of galaxies. And so our knowledge of the content of our universe has magnified by orders of magnitude. And of course, these galaxies, it was discovered by Edwin Hubble, the famous astronomer in the early 20th century. He was able to measure the distance to galaxies and also the speed with which they were moving towards us or away from us. And what he discovered was, on the average, most galaxies are moving away from us. And moreover, the farther away from us they are, the faster they're moving. And that led to the idea of the Big Bang, that the universe started as a very condensed matter and everything expanded. Of course, we all knew and have known for many years that everything in the universe has gravity. So this expansion is gradually slowing down. But we want to measure the rate at which it's slowing down. And it turns out that the farther away the galaxies that you can measure, the more precisely you can measure this rate. We had never been able to determine this before Hubble. But Hubble had the ability to look at these supernovas. You can see here's a galaxy which is normal, and then a star explodes as a supernova, and we know enough about supernovas that we can use that to determine the distance to the galaxy far, far away, as well as the speed that the galaxy is moving. And using this, the astronomers could determine the rate at which the expansion of the universe was slowing down. This was one of the primary observing tasks for Hubble, and it was given to 2 independent teams of astronomers. And they didn't publish their results for a long time, and everybody was, why aren't they publishing? And the reason was because both of them discovered something that they couldn't believe, but when they finally compared results, what we now understand is that the expansion of the universe is not slowing down, it's accelerating. There's some strange force out there that is opposing gravity, and we've come to call it dark energy, and it's nice to give something a name because it makes it sound like you know what you're talking about, but in fact, we don't have a clue what dark energy is about. But what we have discovered using some other astronomical observations is that dark energy accounts for almost 3/4 of the content of our universe. And that dark matter I talked about is almost 1/4. So for all of you students who have worked hard learning physics and chemistry and biology, I'm very sorry to tell you that that relates to about 4% of the universe. And the rest of it, that's what makes science exciting. For every problem you solve, new problems arise, and unraveling this mystery is going to be really exciting for the astronomy of the 21st century. So here's the final result of the story of Hubble. And the message that I want really to leave you with is that it's not just that you can fix things when they break. It's the fact that we could service the Hubble and continually upgrade the instrumentation that has made it so scientifically valuable. And that as we have learned what we can do working outside in spacesuits, we've been able to do more and more complex tasks, and that's what has made Hubble so incredibly productive. Hubble is the last servicing mission, left it as good as new. It's up there, it's still doing its thing. And just looking ahead, you may know that NASA is working now on not really a replacement for Hubble, but another type of a telescope which is even more powerful, larger. It will be able to see things even farther away than Hubble can. It's the Hubble Space Telescope. It, like Hubble, very complex. It's over budget. It's behind schedule. Hopefully it's going to be launched late next year. It's being worked on at that same clean room in Goddard where we trained for so long for Hubble. That's each one of those mirror segments. Remember I told you that Hubble basically took the telescope technology of the mid-20th century, one large glass mirror, and put it into space. In the later 20th century, astronomers developed multi-mirror telescopes, and this is the technology which is going to be put into space with the Webb telescope. The mirrors are made of much lighter weight beryllium, and they each have individual focusing apparatus so that it's not going to be out of focus when it gets up there. But it is huge. This is a full-scale model. And you can see it's so big that you can't launch that as a whole telescope under the shroud of any rocket. So the whole thing has to be folded up. And it's not going to be put in orbit around the Earth. It's going to be put about 1 million miles, 1.5 million kilometers away from the Earth in the direction just opposite the sun, and that's where it's going to be working. And on its way out there, it's going to have to gradually unfold itself, and I can guarantee you there's going to be a lot of white knuckles while all that deployment is taking place. Well, that's for the future. What I hope I've left you with is the story of the Hubble telescope and the part that I was fortunate enough to play in it, something that I'll never forget. And I hope you can see I love talking about it, and I can't tell you how many times I've talked about Hubble, but what I love is that every time I talk about it, it sort of brings it back, and I've been a very lucky guy. And there's Hubble, and there's me, sort of waving to everybody and saying thank you for your attention, and I hope you enjoyed it.
Thank you very much for the enlightening lecture. It's very interesting. So, if we turn the lights on, and I would like to open the floor for questions. If you have any questions, please raise your arm.
Is it possible to turn the lights on so we can see the people who are asking the questions? That would be nice. So you're not all sitting in the dark. Just ask the question, I'll repeat it. Okay.
Good evening. Thank you for your great presentation for the Hubble. As we know that, in fact, the astronauts have taken several change of the parts, like the mirrors, sensors, and even the solar panels. So my question is like this: which part of the change, in your opinion, is the most difficult? Yeah, as we think that the solar panels have a so big area, and even I think it's a little flexible. Yeah.
It's hard to say which is the most difficult because each of those tasks involved different skills. When you're moving the solar panel around, yeah, it's very big. It has a lot of inertia. You have to move it very slowly, be very careful that you control it so it doesn't go out of control. When we were inserting the wide field camera, there's a very tight tolerance and you don't want to bang it, so you have to be extremely careful. On the other hand, some of the small things that we were working with require real precision, and we're using really bulky gloves like those tiny screws I was talking about. That was for us, I'd say, the most difficult task, working with all those tiny screws, because they weren't designed to be operated on with a spacesuit. And I would say we both decided that was kind of at the limit of what we were capable of doing working in a spacesuit.
Yeah, thank you, sir, for such an extraordinary lecture. My question is that Hubble broke the myth that once you put something in space, we cannot go and repair it. And that is what happens with ordinary satellites. So my question is that why was it done that way? I mean, why was it planned that there will be service missions? For example, in James Wave, we are going to put it in orbit like L2, and you cannot generally go and service it there. So,
well, the problem with Webb, we right now do not have the capability of putting astronauts 1.5 million kilometers away from the Earth where they can work. Also, there is an expense in designing a telescope to be serviceable. I think we showed that in the case of Hubble, it was more than worthwhile, because what we really had, as I said, every time we visited Hubble, it was like having a new telescope. So we really got 5 Hubble telescopes for not quite for the price of one, because we had to pay for the servicing missions, but they were a lot less expensive than building a new telescope every time you went up. We all hope that Webb will work, and of course Webb has the best detecting instruments that are available right now. If it's up there for 20 years, it will no longer be state-of-the-art, but that's just the way it is. And maybe by that time we'll be able to go and do something there, but it definitely is not designed for servicing. Hubble has been unique in that respect.
We have a question on this side of the room.
Yeah, thank you for your talk. We've seen like a couple of sequences where you were in daylight and then like on the back of the Earth, which was in the darkness.
Mm-hmm.
Does NASA account for these like in your training? So do you train for working in daylight and on the other side? And does it make a difference? Is it more difficult to work in the dark?
Yeah, that's a good question. We do have lights on our helmets so we can work in the dark. And actually one of the things that we did when we were working in that big clean room at the Goddard Space Flight Center, we actually they had a full-scale, high-fidelity mock-up of Hubble. And we took both the wide-field camera and that corrective optics package, and we installed them several times. They had to be suspended by a crane, of course, because here on Earth they have weight. But we did it with the real instruments. And one of the things that we asked them to do, we want to see how much visibility we have at night. And it was a big thing for the safety people because they didn't want to turn off all the lights in that big room for safety reasons, but we got them to agree to do it. One of the things about training for Hubble, especially the first mission, it was so critical that we could get people to do things which normally they wouldn't have been willing to do. And so they did turn off all the lights, and all we had was the lights on our helmet because we wanted to see, you know, if somehow on putting it in, it got stuck, how much would we actually be able to see? Would our lights be able to actually show that? So yeah, we actually did. When we're working underwater, no, you can't really turn out the lights. So that was really unique, the ability to see that at Goddard in the clean room. It's not something you normally do.
Another question there?
At 600 kilometers above the Earth, there's still a bit of air. So does Hubble have to station keep? And did you have to? Did
Hubble have what?
Does it have to station keep? Like, does it need any fuel to fight the atmospheric drag?
One of the reasons we put it as high as we did was to minimize the atmospheric drag. Yes, it does gradually come down, and every time the shuttle went up to visit Hubble, one of the last things that we would do before releasing it was to raise it up a little bit so that it will stay up as long as possible. So yeah, it doesn't have its own propulsion, but we did that with the shuttle. And you know, it'll be up there for a long time, even if we don't do anything about it. But we don't want it to fall down uncontrolled, because as I said, it's not going to all burn up. And we have to, eventually they'll bring it down and drop it into the Pacific Ocean, which is where we want to put the big space junk.
Okay, another one there.
Hi. On one of your other missions, you deployed the Italian tethered satellite.
Ah, yes, the tethered satellite.
Can you explain the science behind that and maybe what went wrong?
Oh gosh, lots of things went wrong with the tethered satellite. I don't really have time to talk about that in detail, but just so people know, this was a satellite which, unlike all other satellites, we launched it out of the shuttle, but it remained attached by a long tether wire, about 2 millimeters in diameter, and we extended it out to about 20 kilometers to do various experiments with it. Unfortunately, the tether broke because it had a short circuit in it, but while it was out there, it's a sight that I will never forget. I mean, standing up there and seeing this, the tether was white on the outside and the sun reflected off it, and this tether going up 20 kilometers sort of into nothing. If you know the story of Jack and the Beanstalk, that's the way I felt. You know, Jack standing looking up at this beanstalk going up into the heavens. It was an incredible sight. Very frustrating that it did break, but. Yeah.
So one more question there, and then we'll move to the middle.
Do you miss being in space?
What?
Do you miss being in space?
I didn't understand. Do I miss being in space? Boy, I would go back in a minute if I had a chance. Please don't tell my wife. She doesn't want me to go back. But it's a great privilege, I have to say. I mean, I've been a lucky guy. Up until this point, only about 550 people have ever been in orbit. We hope that over the next 10 years, with some of the commercial space activities, which a lot of you students will be hearing about, that number will be much larger, because I think it's really an extraordinary experience, and I'd love more people to be able to have it. For now, I've been very lucky to have it, and as I said at the end of my talk, I still love talking about it because it sort of brings it back, and I love sharing it with as many people as I can. So it's been a real pleasure sharing it with you tonight, and thank you all for coming.
Thank you very much. On behalf of the Space Studies program, we have a small gift for you here, and thank you for your time.
It's the Earth. Thanks.
Thank you very much. So there's going to be an opportunity for pictures. So if you form a line here for a little bit, and our guys will start guiding you here.
Photo? Yeah, photo. Yes, just a minute.